Okay, such beautiful, slides, Gino.
Yeah, thank you.
I didn't know you know to do something so nice. I mean,
All right.
how do you do it? It's a spatial type of.
Yeah, I mean, I like pen more than keyboard. So.
I see. Okay, good. What's the exact time now? I mean, my clock is maybe not too exact. I'm not sure. Let me look at my cell phone.
I'm going to drop by S101 and see if anyone's waiting there for a talk that's not going to happen.
Yeah. I think if that's the case, they can just came to the Wolferson Hall.
Yeah, we still have one or two more minutes.
Mm-hmm.
So.
Alex, why are you not in the lecture hall?
Why not in the lecture hall? Because there is an ongoing conference now at the Institute in analysis. So they took the room for the whole week.
Okay, too bad.
Yeah, but that's okay. I mean, I will announce in a minute. I'll talk about that, and we will compensate it, at least for the local people.
The same amount of people. Yeah, the speaker is missing obviously, but at least we have slides, so we can.
Yeah, I see some people are entering. Yeah.
No.
Yeah, why not?
Okay, so I believe we can start. Just before we're starting, so we are going to hear the talk by Jinbo Ren on bounded generation via the Diophantine geometry. Will present his breakthrough work, which was kind of against the expectations of many of us, showing that uniform lattices are not bounded generated. Unfortunately, we cannot meet today, for the local people, unfortunately, we cannot meet today at the usual seminar room because of a conference going on this week here in the Institute. But to compensate for that, the local people are invited to join. We'll go immediately after the talk, really immediately, we'll meet at the dining hall and we'll try to sit together for a more informal discussion of after the talk. So I apologize for the people from the outside the Institute that I cannot invite you to join this lunch. On the other hand, I can invite you to join starting next week, a sister seminar that is going to happen every Wednesday from 10 till 11, or let's say more precisely, maybe to 10 till 10:50 to enable a few minutes break, which will be somewhat related to this conference, and I will send announcement about that, about the other seminar to all the people who are getting. Anyway, the messages about the arithmetic group. The other seminar will be called character varieties, dynamics, and arithmetic. There will be some connection between the two seminars, but they will be independent. So all are invited, and it will be by the same format. You know, it will be hybrid. Some of the talks will be inside. Some of it will be the talks only from Zoom. Okay. So after this introduction, Jinbo, the stage is yours.
All right, thank you, Alex, and thank you for joining this talk, my dear friends. Today, I'm going to discuss joint work with Korvaya, Robinchuk, and Zanier about some results of bounded generation while Diophantine geometry, which is new. So if you consider the method. So this talk is no doubt a continuation of Professor Robinchuk's talk 2 weeks ago. So let me just briefly recall the definition. So we say that let gamma to be an abstract group. And we say that this gamma has the property of bounded generation. And let's use a letter BG to abbreviate that. So if there exist finite many elements, gamma 1 to gamma d, and they are not necessarily distinct, such that this gamma can be written down as the product of the cyclic subgroups generated by these elements. And this definition obviously has a profinite version. Suppose this gamma is a profinite group. That means we have topology here. Then we can consider the BG pro. So everything is the same except that this gamma can be written down as the product of the closure of the cyclic subgroups generated by these elements. And as you can see that both BG and BG pro, they are purely combinatorial definitions. Well, they have connections with many other branches of mathematics. So since Professor Robinchuk already mentioned this in his talk, so let's just briefly mention this. The first one is something I'm going to use again. So let me just say BG and also BG pro. So this has close relation with the sex congruent subgroup problem. So let me mention that. So Platonov, Robinchuk, and independently Lubowski. So they show that under certain conditions, bounded generation implies congruent subgroup problem. So that means this bounded generation serves as a potential strategy to attack this congruent subgroup problem. And of course, Yehuda Shalom used bounded generation to compute some Cauchy property P, and Shalom-Willis to verify certain cases of Marquis zebra conjecture, and Robinchuk verifies some semi-simple rigidity. So for more information, you can watch Robinchuk's talks 2 weeks ago, and also his seminar talk on May 6th. And obviously, you are welcome to read our paper and references therein, and all comments are warmly welcomed. All right, so this is the background. And now let me just explain how we are able to arrive at the formulation of the main theorem. So the starting point is quite elementary. So we just look at some rather simple examples of groups with bounded generation. So the first observation is that bounded generation obviously implies finite generation. Well, obviously the converse is wrong. But if you require this group to be abelian, then this converse becomes true. So then we just wondering, well, if this group is not abelian, but in some sense not far from being abelian, does this property plus finite generation implies bounded generation? And so let's just recall this inclusion. So in group theory, abelian groups are always nilpotent, and nilpotent groups are always polycyclic, and polycyclics are always solvable. So these groups are all groups which in some sense not far from being abelian. So for instance, if you consider solvable groups, that means you take the commutators, then you take the commutators, then you will get the trivial group in finite many steps. So this is the solvable. And if you get a trivial group in one step, this is abelian. And similar, you can see these are not far from being abelian. And you can show that the finite generation plus nilpotent is bounded generation. Finite generation plus polycyclic is bounded generation. However, one example in our paper shows that finite generation plus solvable does not imply bounded generation. Well, of course, in certain situations, yes. So for instance, we see that by a result of Marcev, all the solvable subgroups of GL and Z are polycyclic. So that means the solvable subgroups in GL and Z finite generated implies bounded generation, but not true in general. So in our paper, we give this example to be the so we consider this A to be an integral Laurent polynomial and X just to be some power. You can show that this is solvable and finite generated, but has no bounded generation. But still, let's just keep in mind that more or less we want to find a connection between bounded generation and solvable property. And eventually, so this is part of our main theorem. All right, so now let's give more motivation to our main theorem. So one natural question is, okay, so as I mentioned earlier, so bounded generation has a lot of applications in other areas. So let me formulate the main question. So we ask whether bounded generation can possibly hold for an infinite as arithmetic subgroup or an anisotropic simple algebraic group. Anisotropic means a lack of unipotent. So why we formulate this question? So there are several motivations. The first motivation is that, well, if you consider all the known examples of S arithmetic groups have bounded generation, so for instance, SLN, O of S, etc. So you can see that none of them are anisotropic. So we're just wondering whether anisotropic situation is possible, to give bounded generation at all. The second, so as I said, BG bounded generation has connection with congruent subgroup problems and rigidity, etc. But in many examples of congruent subgroup problems, rigidity, the unipotent elements plays a crucial role. In other words, they help us a lot. So we're wondering, so if there is, we don't have non-trivial unipotent elements, then what's the situation? That's the second. The third motivation is the most intuitive one. So let's consider the 2 times 2 matrix. This one is unipotent. And if you consider the growth, the nth power, well, you just get something like 2021n, which is a linear growth, quite slow. But if you take this semi-simple elements and you take the nth power, you get exponential growth. So you see exponential growth, this is grows much faster than this unipotent elements. So intuitively, the semi-simple elements are rather sparse. So sparse means that, well, in other words, exponential growth gives a very sparse distribution. So it is unlikely to generate the whole group. So this, generates our expectation that the answer to this question should be negative. And of course, we see that anisotropic. So most important ingredient of being anisotropic is we want some bounded generation by semi-simple elements. So that means we don't want unipotent elements up here. So we are able to formulate a more general version of this response of this question. So here comes our main theorem. Okay, here we go. The main theorem. So again, this is joint work with Pietro Crovaglia, Andrei Rapinchuk, and Umberto Zanier. So let's see. I mean, so we consider a linear group. That means that gamma be a subgroup of GL and K to be characteristic 0. So suppose this gamma has bounded generation, such as all the members participating in this BG are semi-simple. So that means we only allow sparse elements joining in this product. Then this gamma must be virtually solvable. So let's just recall that you know, we want to find some connections with solvable and BG. So this condition just tells us, you know, if bounded generation by some sparse elements, then it must be virtually solvable. But I must emphasize that this is not a criterion. So for instance, the example on the previous page, so this tells us, you know, solvable, you know, does not necessarily imply bounded generation. So that means this one is not a criterion. However, so in an anisotropic case, so which is the case we are interested in, so this is indeed a criterion. So our claim is that if you consider an anisotropic linear group, gamma inside this GL and K, then the bounded generation holds. Of course, in this case, bounded generation is automatically bounded generation by semi-simple elements. So this is equivalent to say that the gamma is finally generated and virtually abelian. So that means it's almost the trivial case. So that means for anisotropic, bounded generation is always the trivial case. And a more interesting corollary is the following. So we consider the S arithmetic groups. So this is indeed the negative answer to the question on the previous page. So let me just give a complete description. So we say that if you have infinite S arithmetic subgroup of a simple anisotropic algebraic group, then it never has bounded generation. So I mean, let's say, although I give a corollary in the name, this is crucial because of this corollary. So the approach of using bounded generation to attack congruent subgroup problems need a modification, as I will mention later. All right, so this is not the end of the story. So our main theorem also has some other you know, interesting byproducts and consequences. Let's see two of them. The first one is, well, it's easy to see that if an abstract group has bounded generation, then if you take the profinite completion, then you get BG Pro, the profinite, you know, bounded generation. So that means BG implies BG Pro for the, you know, for the profinite completion, and the converse, you know, so that means whether the BG Pro for gamma hat implies the BG for the original group. This one has been open for a while. And in our paper, we are able to answer this question. So why is that? That's because if you consider some examples which a congruent subgroup property holds, you know, anisotropic groups with congruent subgroup property, then this will gives a negative answer. So because the work of Platonov, Rapinchuk, and Lubovsky, they show that under certain conditions, BG Pro is equivalent to congruent subgroup problem. So that means this examples gives a negative response to this question. That's a very interesting byproduct. Another byproduct is something people care in algebraic geometry, which is a polynomial parametrization. So polynomial parametrization means for certain integer points or as integer points of an algebraic variety. So we want to find a simple polynomial parametrization. So for instance, let's consider this Pythagorean you know, triangle equation over Q, for instance. And so we know that, so there is a classical polynomial parametrization, which is this one and union this one. So in general, we give two systems. However, due to a very interesting paper by Versenstein 11 years ago, so it was shown that one system is sufficient, and I recommend that you look at this paper. All right, so now let's go to bounded generation. This question, polynomial parametrization, is closely related to polynomial parameterization, bounded generation. So let's just consider this SLN O of S, where OS is the ring of S integers. So let's mention the name of Carter, Keller, Morgan, Diophantine, and Surrey and other authors, a long list. So the fact is that this guy has bounded generation if n is larger than 2 or n is 2 and the S units is infinite. So in this case, you can show that this bounded generation can be given by elementary matrices. So by elementary matrices, then you are able to give this polynomial matrix in SLN and with polynomial coefficients, such as if you specialize at these S integers, you just get the whole group. Well, let's just recall that due to our main theorem, this one does not have bounded generation by only using semi-simple elements. So that means we must need unipotent. So what does that mean? That means if you consider the exponential polynomial parameterization, so at least the product of cyclic groups doesn't work. But still, we can ask whether other kind of exponential parameterization is possible to for this group. So this is something we are interested in. All right, so let's now go to the proof. So the proof consists of 2 ingredients, so which I'm going to explain. But before we start, let's just explain why this results. Has some difficulties. The main result is the following. The main difficulty is the following. So let's suppose this gamma is not virtually solvable. Then we want to show that this semi-simple cannot generate the whole group. So we want this one to be not the whole group. So that means we want this guy to be small. Well, I mean, this is a trivial estimate. So that means if you consider the power to be from minus t to t, then we know that this is somehow a polynomial growth. But this one is not good enough. We want this guy to be much smaller than this polynomial growth. And this expectation makes sense because if you take the multiplication of matrices, you can expect that a lot of cancellation happens. But how to control this cancellation? This is not easy. And at least, quite complicated. Well, but there is one thing. If cancellation is something we cannot control, we find something we can control, so which is the eigenvalue. All right, so here comes the key observation. This key observation, so let me just read it word by word. Suppose you have 2 square matrices, M1 and M2, and suppose these 2 matrices are equal, then they must have the same set of eigenvalues. Well, of course, somebody might ask, hey, do you think this is really useful? Because this is so trivial, right? Of course, if 2 matrices are equal, they must have the same set of eigenvalues. But my response is, it is true that this is trivial. This is far from superficial. This is a key observation, for us to prove the main theorem. All right, so now let's see. In practice, we have 2 matrices which will appear in our proof. So they have different, algebraic expressions, very different algebraic expressions. And now we compare the eigenvalues on both sides. So you will get some Diophantine equation, which we have the tools, to handle. So you can get some special structures by Lohong's theorem and to get what we want. So this key observation, so we are going to use it. I'm going to emphasize this during the proof. All right, okay, so compare the eigenvalues. But compare what? Of course, eigenvalues has a lot of properties. Compare what? So this has 2 ingredients. One ingredient is Diophantine geometry. Another ingredient was the notion called the generic elements. So let's outline.
Can I ask a question real quick?
Yes.
Do you really? I'm a little confused. You're saying if you take R random matrices and you look at their products the way you wrote, do you really expect cancellation, or do you just expect like a few? Do you expect small height? Or I'm confused by what you mean by control cancellation.
Well, I mean, we expect this guy to be small. That means smaller than the ambient group. So we expect that the growth is slower than this rate.
I would put it a bit differently.
I see.
If you're counting the number of matrices in a box, you can do that globally. But then when you start counting locally with your semi-simple elements, those are growing, those words are growing very large, so that if you're going to achieve the elements, there has to be cancellation way out there to bring it back to be small. And that's the way
I'm confused because it says theta I less than or equal to t. So you're just considering small word length, but then I don't, but like the height of this product could be very, very large, right?
Right.
Okay, I'll think about it.
I think the eigenvalues will clarify that.
Okay.
Yeah, so that means, I mean, if you count this one, I mean, it's not easy to count this directly. I mean, with respect to height or something else. But I mean, if you look at the eigenvalues, then we can do it. You know, so that's the key observation. I mean, yeah. All right. So now let's see why this is sufficient. I mean, this so trivial observation make us prove the main theorem. Here we go. So this depends on two ingredients I'm going to explain soon. Ingredient 1, which is Diophantine geometry. Ingredient 2, which is generic elements. So let's give an exponential analog of linear independence. So if you consider A to be an abelian group, and if you take R elements, AR from AR in A, and we say that A in A is multiplicatively independent from those A1 to AR. So if this relation holds, so that means if this one can be written as an integer, I mean, as some product of some powers, then this E must be equal to 0. So let's say this definition automatically implies that this A is torsion-free. All right, okay. But I mean, this is just called multiplicative independent. All right, so now two ingredients. So for Diophantine geometry, so which is the torus version of the Mordell-Long conjecture. So, so if you consider gamma to be a semi-simple element, and we are able to do that. We are able to show that each eigenvalue of gamma is multiplicatively dependent from those of gamma 1 to gamma r. So of course we can write things more explicitly. So that means if you write these eigenvalues of gamma I to be lambda I1 to lambda In, and if you take lambda to be an arbitrary eigenvalue of gamma, then there exists a non-zero integer E and some integers Eij, such that this multiplicative dependence relation holds. Well, of course, I mean, if you are familiar with the Mordell-Long, you already know why this is true, because something is a special subvariety given by this form. I will explain this later. All right, ingredient 2 is called generic elements. So which says that, I mean, so if this group is not virtually solvable, then you can always reduce to this situation such that there exists a semi-simple element whose eigenvalues are multiplicatively independent from those of gamma 1 to gamma r. And of course, these two conclusions are, cannot coexist. So why is that? That's because you assume that this gamma to be non-virtually solvable, but with bounded generation by semi-simple. So that means this assumption is wrong. All right, so this is the whole picture. And now let's go to these two ingredients respectively, and to convince you that's why this is true. All right. So the generic elements, this is shorter. So let's do generic elements first. So this theory was developed by Prasad, Rapinchuk, and also other authors, Lohan Zhuv, Emanuel Kowalski, Gortnik, etc. There are many authors, but let's only give one version. So here's our setting. I mean, so in that, this K can be arbitrary, but in our talk, so we are only interested in K to be a field of characteristic 0. But in this discussion, for the definition of generic, we don't need that. So we consider a semi-simple algebraic group over a field K, and you consider a maximum K torus called T. And then you know that the absolute Galois group has a natural action on the character group chi T. And this one will leave the root system phi of phi GT invariant. So that means this gives a continuous group homomorphism. I call this a rho of T. So our definition is that a maximum K torus T, just like this, is called K generic or generic over K. So if the image contains the wire group, so the group generated by the reflections of the simple roots. So, and if you have this definition, and then we consider a regular semi-simple element. Regular means that the dimension of the centralizer is equal to the K rank. So a regular semi-simple element gamma in the G of K is called K generic. So if this torus, if you take the components of the centralizer, is K generic as defined here. Let me just briefly explain why this notion is called generic, and then we proceed. So this one related to the classical Galois theory. So if you consider an integer polynomial to be a monic and irreducible, then typically the Galois group, so which is the splitting, if you consider the splitting field over Q, and you know this is a group, so can be realized as a subgroup of the symmetric group, and you can show that typically that means the exception is small. This Galois group is equal to the symmetric group of D elements. So in fact, we have this asymptotic description. So compare if you count the heights.
Jinbo, just a little bit slower.
Yes, of course, yeah.
What is, sorry, I missed something, maybe what is SF of P?
Which is the splitting field of P.
What?
The splitting field of P.
Okay.
Yeah. So basically, we say that, so in general, the splitting field, I mean, over Q has Galois group exactly equal to the SD.
Usually, yeah.
And of course, we have this more concrete description analytically. So if you consider the polynomial of height at most T, then this is the number of all such polynomials. And we show that this Galois group equal to the largest possibility is almost everything and plus some small error terms. So our case is similar. Our case is similar. So you can show that. So one sentence is wire group is generically the Galois group. And let's make things more precise. Let's consider the number field case, for instance. If you consider this gamma to be an element in this arithmetic group, where S is a finite subset of places containing all the infinite ones. And if you consider the field generated by the eigenvalues of gamma, so this is the analog of this polynomial P, SSFP. You can also consider the intersections of the splitting field of all the maximum K tori of this G. Okay, so now this one is the generic Galois group. So this is the subgroup of the automorphism of the character group generated by the action of the wire group, and also this absolute, and this Galois group of KT over K. KT is the splitting field of the torus. Then you can show that typically this wire group is the Galois group of this extension. And for this K of gamma over K, so this is the Galois group you're interested in. So this is exactly the group generated by the Galois group and the wire group. So that's why.
Sorry, you only need the existence of a generic element, but in fact, you're saying you prove it by this counting argument by like sieving, like Gallagher, or you're just quoting it as a. What do you do in your paper?
There are some people using large sieve to prove that the generic elements are, almost.
Okay, so you're quoting the theorems of maybe Lubotsky and Kowalski and people like that, and Riven.
Yes. Well, I mean, we don't need that. We only need existence of
Yeah,
generic
right,
elements.
but that's
So-
what I was asking you. I was saying, are you just pointing out that the way you can get the existence?
Yeah, I want to explain why this is called generic. Yeah, that's why
Okay, okay,
that's why I'm
okay,
doing
fair
it.
enough. I'm glad you're using that. That's
Yeah.
nice.
Yeah, and by the way, so this generic is closely related to Hilbert irreducibility. So as Dennis talked last week. All right, so let's. I mean, of course, I mean for this, abstract case, we can also prove some counting properties, as Peter pointed, but we are not going to use it. So this is all we need. So let's see how we use generic elements. So what we want is virtually solvable group doesn't have bounded generation by semi-simple. So by some standard group theoretical tricks, quotient by the solvable radical, etc. So you can show that if you take the Zariski closure of this group and take the connected component containing the identity, then you can reduce to the case that this group is a non-trivial semi-simple group. And this is exactly we are going to use the existence of generic elements. Okay, so here this is the key property, and as I promised, yes. So as I'm promised in the ingredient 2, by using generic elements to be multi-predictively independent. So let's give a more precise formulation. So in this case, that means this gamma such that this G0 is a non-trivial semi-simple group. So in this situation, so if you consider a so then we can show that, yeah, this is the existence of these elements to be independent. So there exists a semi-simple element gamma, which is in this group and also in the identity component, whose eigenvalues are multi-predictively independent from those of gamma 1 to gamma r. So this is the ingredient 2. We don't need more. We don't need anything about the density or something. We only need the existence of generic elements. So, which is done by Prasad and Rapinchuk. So they prove that. So that's gamma and G as before. I mean, we also need a K as a finite generated field, but this can be overcome. So let's just briefly say gamma G as above. Then this gamma contains a K generic element. So we only need the existence. And I will explain why this K generic elements is sufficient for this proposition. So of this multi-predicatively independent property. Let's see how. Let's give a proof sketch. Well, I mean, we're not going to use the K generic, but we are going to use the generic over a larger field. So which is the L generated by the eigenvalues of this gamma 1 to gamma r. So this is the field we are going to work with the generic property. And now by the previous by the theorem of Prasad and Rapinchuk, so we can find a regular semi-simple element gamma, which is L generic. And my claim is that this one is sufficient. Well, I mean, so for the torsion-free, this is easy. You can use the Selberg's theorem to find a Zariski dense subgroup, a finite index, which is neat. So that's not a problem. So now let's verify the multi-predicative independent. So again, for this gamma, if you denote all the eigenvalues to be lambda 1 to lambda n, we want to study the first eigenvalue. Let's call this lambda. And we consider the eigenvalues of this lambda I1 to lambda In. So this just generates the field L. So as defined here. So we want a multi-predictive independent, right? So we just suppose you have this relation, and we call this a common element to be Y. All right, so let's look at this. Y is equal to this guy. So that means, I mean, this L is generated by this thing. So that means this Y is in the L cross. But for the left-hand side, it's just some power of this lambda. So we know that this Y is equal to this chi of gamma for some character in the centralizer. All right, so now we are going to use the generic. So you can consider every element in the Galois group, sigma, and you can show that this one, let's say, I mean, this is one in the L cross. So you can show that this sigma chi evaluate at gamma is the same evaluate at gamma of chi at gamma. But you can easily show that this gamma, you consider the cyclic group generated by this gamma. This one is indeed a Zariski dense subgroup of this torus. So that means this sigma just fix all the characters in this of this torus. But we know that this torus is algebraic, so that means this character must be trivial. So that means this y must be equal to 1. So we just get the multiplicative independence property by using the generic elements. All right, so this is the second ingredient. So now the first ingredient, which is the Diophantine geometry, which is the main novelty of this paper. So I'm going to explain now. All right. So for Diophantine geometry, so let me first mention a very general principle. So the principle is here. So if you have some equations, over some field, so which has too many special solutions, and special depends on the specific situation. So if this equation has too many special solutions, or let's say if this algebraic variety contains too many special points, then this equation must have some special shape, or this algebraic variety must have some special shape. So for instance, we know that, so if algebraic variety has too many rational points, then you can make this algebraic variety defined over Q bar, over Q. This is the Lagrange interpolation, for example. All right, so the key result I'm going to mention is the Lohans theorem, which was the conjecture by Serge Lang in 1960s and proved by Michel Lohan in 1984. So let's keep a statement. So we consider V inside the Q cross N, so which is the Q bar point of the split torus. And we consider irreducible subvariety, V. And our claim, so suppose that this V contains too many S unit points. So too many means, so Zariski dense. And what's the meaning of S unit point? S unit point means that all the coordinates are S units. So as this general principle suggests, this equation, this variety must have a special shape. That means this V is indeed the zero locus of finite many polynomials of this shape, x1, I1 until xn, in equals to eta. And this eta has all the components to be a S unit. You can also formulate this conjecture, this theorem in this way. So which says that, so this OS cross N, the N tuple of S units. And if you consider any subsets of this OS cross N, that means if you consider any special set of special points and you consider the Zariski closure, then you can get finite many components. Each component is the zero locus of this shape. So what does that mean? That means generically, the algebraic relation of this S units must be multiplicative. So this is the meaning of Lohans theorem. Well, of course, you can formulate Lohans theorem in a more geometric way. So which means that if this V contains too many S unit points, then this V must be a translate of an algebraic subgroup by S unit points, which is a coset by S unit points. And this theorem is.
I'm a bit confused here. Mm-hmm. You look at this V inside the Q bar to the N, mm-hmm. You have some assumption about too many, right? But now, if you will take O, the O integer, the O to be large enough, and S to be large enough, so this is going to be always going to happen, isn't it?
Well, S is fixed. S is fixed.
What?
S is fixed.
Ah,
So
You have a finite, in terms of a geometric statement, you have a finitely generated subgroup in the torus,
Yeah.
if you want to state it that way. But that the bounds depend on the number of generators. And
yeah, so that means this S, we must fix some S to formulate this theorem.
I see. I see.
Yeah.
Hey, Jinbo, real quick, could you clarify for me where eta lives? It lives
Which
in
one?
O
Sorry?
star S to the N.
Where is it? Sorry.
Where does eta live? I mean, eta looks to me like it should be a scalar based on the equation, but are you
Yeah,
saying that
I
eta is
mean-
an nth power, or is that it's an n tuple?
It's an n tuple of each component is a S unit. So basically, if you let eta to be 1, then this is just some algebraic subgroup. And if you let this eta to be something else, then this is just the translate. That's a coset, you know. And this eta is the elements, one element.
in fact, by a torsion point.
It's not necessarily a torsion point. I mean, so this is the, I mean, torsion point is another formulation in the next page. But for this one, it's the,
No, you're right. You're right. Sorry.
yeah, it's
But you are, one point you're making, yeah, which I think I discussed with you once, using Schlichterwey for some uniformity. Laurent didn't use Schlichterwey. Schlichterwey came later with the subspace theorem, which is uniform over number fields. So you don't need that, right? In this work.
no.
Yeah.
I mean, we fixed the number field and we fixed the,
Right.
you know, we fixed the S.
So why
So
are
that
you
means for
mentioning
any number
Schlichterwey?
field,
So why do you
Pardon?
put Schlichterwey?
well,
Are you just
because
stating the most general?
the original subspace theorem is just for the usual Euclidean norm. For Schlichterwey, he's using this p-adic norm. We need
okay.
p-adic version of the subspace theorem.
Okay, thanks. Okay.
Yeah. Okay, great.
So Jinbo, could you clarify x1 through xn? Are these scalars or are they n tuples, or? I mean, how should I
X1
interpret?
and xn, they are just variables of polynomials.
Okay, but then when you take the zero locus, are you thinking of them as elements of
Yeah,
some
that's
bar
right. So this
star?
B is the zero locus of finite many such polynomials.
All right, I'm having trouble
Or-
parsing how the left-hand side is not a scalar. I mean, maybe I'm just
It
being
is a
stupid with
scalar
notation.
if you want. We use
So if the left-hand side is a
multiplication.
scalar, why isn't the right-hand side a scalar?
Pardon?
I mean, you're saying that eta is a vector, eta is an n tuple. The left-hand side looks to me like a number.
Oh, you are right.
Maybe
you
I'm
are
being
right.
very stupid with
sorry,
notation,
this
but
eta is must be in the OS cross. Yeah, thank you. You're definitely
oh,
right.
okay, cool,
Thank you.
great.
Yeah, thank you. Yeah,
Thanks, Jinbo.
yeah, thank you so much.
Paul, I think the easiest way to think of it is you have this variety, and it's originally any subvariety of this torus. But then if you have too many points, then the subvariety has to be a subtorus or a translate thereof.
Yeah,
Okay.
that's exactly this shape.
That sounds good. It makes sense. Yeah.
So that means if this subvariety contains too much special points, it must be a coset. That's the Lohans theorem. All right. Okay. So again, as I said, if you have a subset of special points and you take the Zariski closure, then you get a union of finite many cosets. This is another equivalent formulation we are going to use later. All right. Okay. Can I switch to the next page or more? All right. Okay. So feel free to ask if you want me to go back. All right. So this is the Lohans theorem. I mean, let's explain. I mean, nothing is better than some examples, right? So today is November 3rd, 2021. Right? And our lovely institute, IAS, was founded in 1930. So let's consider this Diophantine equation, right? So we consider M and K to be integers. Then my claim is that this one has only finite many solutions, integer solutions at most. I mean, I guess this one, I mean, it's not obvious. Maybe this is a suitable exercise, suitable problems for the, mathematical Olympiad, maybe. Maybe they can give some elementary solutions. But my claim is that this is indeed a special case of the Lohans theorem. Why is that? So let's consider this number field to be Q. And we consider this S. Oh, sorry, I forgot the infinity. And we consider the 1930 is the 2 times 5 times 193. And 1103 is a prime number. 2021 is the product of 43 and 47. So this is all you need to localize. And in this case, the OS integers is just some multiplications, with this one to be integers. And now, if you look at this star, and you just divide this 1930 to the k, you just exactly get this one to be a S unit, and this one to be a S unit, and equal to 1. Let's say the point is that x1 plus x2 minus 1, this doesn't give a coset. So that means the special point, is not many. It must be finite many. So we are done. So, but we are using some very, big theorem to prove a small result. That's interesting. All right. Okay. So now let's see more examples of the principle on the previous page. So this table, this is far from complete table, but let's just mention something. So, so the theorem is always, suppose you have an ambient variety S, and you have a set of special points. And if you have a subvariety which contains a large set of special points, then this subvariety must have special shape, which is called a special subvariety. Well, for this ambient variety, if this is to be the GMN or A, and if you consider the torsion point, and now suppose you have a subvariety which contains a Zariski dense of torsion points, then it must be a torsion coset. The complete proof was done by Lohan and also Sarnak. For abelian varieties, there are so many proofs, but the first proof was by Michel Renaud in 1983. But now there are so many other proofs. This is a very deep result, of course. And now for modular curves, if you identify this as C to the N with the modular curve by the J invariant, and you consider the special points to be the CM point, that means all components are CM points. And if a subvariety contains a Zariski dense subset of CM points, then this subvariety must be a product modular curves times some CM points. And this is done by the seminal work of Jonathan Pila. Okay, so finally, this is something in the other direction. If you consider abelian variety, which is the abelian analog of the Lohan theorem, and if you consider omega in the AK bar to be a finite generated subgroup, so in fact, you can take the finite rank subgroup. And you can show that if this A contains too much points, if subvariety of A contains too much point from omega, then it must be a coset. So this was first proved by Faltings by using Diophantine approximation, and some simplifications was done by Boita. All right, so now we are able to see how to use this Lohan's theorem. So let's just keep in mind that Lohan's theorem says that we want some set of special points of S unit, and then so we want to consider the Zariski closure of these special points, and they must be given by finite many cosets, which is multiplicative, so which is finished the first ingredients as I promised. All right, let's continue. Okay, so again, so from this slide, you can see our key observation. If two matrices are equal, then they have the same set of eigenvalues. This is trivial, but this is how we prove the theorem. All right, so now let's sketch the proof. So our proof shows that, so for semi-simple elements, this is already enough to get the contradiction. And let's see how. So in this case, we don't need the non-virtually solvable. For non-virtually solvable, which is needed by the part of generic elements, for this one, we just need nothing. So let's suppose that this gamma is bounded generated by semi-simple elements. And we take another semi-simple element, gamma, to be semi-simple as well. So let's recall that semi-simple means that it is diagonalizable in some extension. So what does that mean? That means you can take some invertible matrices with coefficients in a number field such that this gamma can be diagonalized as lambda 1 until lambda n. And we fix the first eigenvalue to be lambda. And for each one, G1, for each one in the gamma 1 to gamma d, you can also diagonalize with eigenvalues lambda I1 to lambda In. Okay, so we assume that this product of cyclic groups generates the whole group. So of course, all the powers of this gamma must be included in this product. So what's the meaning of in this product? So that means there exists some power of A1M and ADM such that this relation holds. And now here comes the Diophantine equation. So we want to substitute this diagonal matrix here and here to this equation. So we get something very big, but big is good because we only need to compare this 1, 1 entry. So for this one, you get this. The left-hand side is just the lambda to the m. So we are going to use our principle. Same matrix have the same set of eigenvalues. This lambda to the m, it must be some polynomials of these eigenvalues of each gamma I, but also with some coefficients, with some entries of this gi. But anyway, they are algebraic numbers, so we are good. So that means if you compare the 1, 1 entry on the left-hand side and right-hand side of this relation, so you can find a algebraic number coefficient polynomial with dn unknowns, so which is basically the right-hand side. So such as this lambda to the m can be written as this expression. All right, so now let's give a fake proof and then give a strict proof. So the fake proof is just one sentence. So if you let m exhaust all the integers, then it has too many. It has too many, so that means this p must be multiplicative. So you get multiplicative dependence. But this proof is wrong because infinite doesn't imply the Zariski dense. But this is not too hard to overcome. Let's see how.
Sorry, Jinbo, can you just say that again? You said it has too many, but I didn't catch like what was supposed to come at the end of that.
Well, I mean, the thing is that this polynomial that does not depend on our m. And so that means we find a lot of solutions, special solutions, which are just the some powers of eigenvalues. And then Longham's theorem tells us this polynomial p must be some multiplicative. But that's not precise, but because the infinite does not imply the Zariski dense. But we can overcome this, and I'm going to show now.
But just to say, what you said that this polynomial, the AI, do not depend on M? I didn't understand what you said.
Yeah. Okay. So this polynomial only depends on this conjugating matrix. So that means, for each power gamma for each power you have some numbers, but this doesn't affect the coefficients of this polynomial. So we just get a family of the special solutions of this equation. So then by Diophantine geometry, we know that this equation must have a special shape. Yeah. So that's
the polynomial depends on the finite, the supposed finite generation. That's what fixes the GIs independent of them.
Well, I mean, this gamma I are semi-simple. So this GI is just the matrix to make this diagonal.
Yeah, right. I'm just saying so there are only finitely many of those. Yeah, right.
Yeah. So that means this p does not depend on m. And when m exhausts all the integers, we get a lot of special solutions. So we expect that this p must be only one monomial. That's our expectation. And let's make things more precise. Okay, so now, so we know that this lambda, this is the first eigenvalue of this left-hand side. And this one, I mean, so we just get a family of special points, so indexed by the integers. But the point is that, I mean, these eigenvalues are just algebraic numbers. They are not necessarily in the OS class, but that's not a problem, because you can always find a number field and a suitable finite set of places such that all the eigenvalues are in the OS class. So that means that in this case, this sigma is just the set of special points, as the formulation of Laurent's theorem. So now we are in a position to use Laurent's theorem. Let's just formulate Laurent's theorem again. Right? Laurent's theorem says that the Zariski closure of any set of special points, in our case, this is our sigma, which is equal to a finite union of special subvarieties. In our case, a finite union of special subvarieties means a finite union of cosets translated by an algebraic subgroup by a S unit point. All right. Okay. So now you consider the Zariski closure of this guy. There are B cosets S1 T1 on Q SB TB, where SL are just some scalars, and this TL is an algebraic subgroup. And now here is how we overcome this finiteness this problem. So we have a family of special points lying inside finite many cosets. By pigeonhole principle, there must be two distinct special points lying in the same cosets. That's the pigeonhole principle. And now, so that means there exists some M1 and M2 to be distinct integers, which are in the same coset. And now we are not far from the multiplicative dependence relation. Why is that? Because if you take the quotients, you just get that this one, this one, and this one, this element must be an element in the subgroup, not only a coset, but a subgroup. But we know that the algebraic subgroups of a split torus is always given by this multiplicative dependence relation. So that means we can find some C and Cij, which are integers, not all zero, so such that this relation holds. And now the only thing we want to make sure is that this C is not zero, because we want something, by our definition, linearly independent, multiplicatively independent. So we want this C to be not zero. Well, I mean, if this if all the such relation, this C is zero, then this T of L must be this G of M times M, where M is the subgroup of GM Dn. So the Dn is just is the part corresponding to the last Dm components. And now we know that, okay, so let's say, I mean, this is our Y minus P of Xij, so which is consisting all the special points. So that means our special point is contained in the zero locus of this guy, but this one is Zariski closed. So you can take the Zariski closure, and this one is a finite union of cosets. That means this particular coset is inside, and we get a contradiction. Why is that? Because in this case, this Y is not a free variable. Y is equal to some P of something, but here this Y is a free variable, so that's not possible. So that means you can make this C to be non-zero. Okay, so we win. So that means this lambda is multiplicative dependent from this eigenvalues. So now this finished the first ingredients. So let's say on the one hand, suppose this group is not virtually solvable. Let's go back to the strategy page. Yes. On the one hand, if you suppose this gamma is not virtually solvable, can reduce to the case that there exists a semi-simple elements whose eigenvalues are multiplicatively independent from those of these elements we want to generate the whole group. However, the Laurent's theorem tells us it's always multiplicatively dependent, so we get a contradiction. But why we get a contradiction? Because we assume this group is not virtually solvable. So we prove our main theorem. All right. So now, so in the rest of the time, so let me just give some quick remarks. So let's go to the very beginning of the slides. So more than 20 years ago, Alex, Andrei, and Vladimir Platonov, they have formulated a result. So which says that suppose the group is good, that means satisfy some condition, called Platonov-Margulis conjecture. Then this profiling version of this bounded generation of this arithmetic group implies is equivalent to the congruent subgroup property. Well, in particular, if you are able to prove bounded generation, then you are able to establish congruent subgroup property. So since our main theorem, so the corollary of our main theorem, this guy, so it tells us you cannot expect to use a bounded generation itself. You cannot expect to use bounded generation itself to produce the examples of congruent subgroup properties for anisotropic situations. But this is not the end of the story, because we have some weaker conditions, which is called a polynomial index growth. Let me just briefly mention. Oh, so this you can show very easily that these conditions can be obtained by the bounded generation, but not vice versa. So this was put forward by I think it's Damzigo. Well, polynomial index growth says that if you consider this, in particular, we want this to be anisotropic as arithmetic groups, and you consider the subgroup generated by the n power, which is the normal subgroup, and the claim is that this this subgroup always have finite index, and this growth rate can be controlled by this polynomial. So that's what we call the polynomial index growth. And also we can even consider a weaker condition. That means we don't need to consider all the m. We just need to consider m and a fixed prime number p and the similar condition. So if you're able to establish this, you can still get this congruent subgroup property. So for instance, for this SLNZ, where n is at least 3, so you can verify this version of polynomial index growth by some purely computation and without using any deep theory from number theory. So that means this one can be a next potential strategy to attack congruent subgroup problem.
Wait a minute. You're saying you can verify this without using elementary matrices?
Well, we need algebraic commutations. Yes, we need.
Yeah, and those involve, I assume, elementary matrices.
Yeah, should be. Yeah. But without using any number theory. So that's what I'm.
Can you say a word? How do you verify this by purely algebraic? How do you verify PG prime?
I never read this paper. I mean, so this is done by Platonov and Rapinchuk in 1992, I think. So I need to check. But yeah.
No, I see why this implies the congruent sub property, but I don't see really easy way. I mean, I would prove it using the bounded generation, but that's not.
Well, but for any topic, we cannot use bounded generation. So
no, but SLNZ. I mean, for SLNZ. No, how would you? My question was, how would you verify PG prime for SLNZ not through boundedly generated? That's what I was asking.
Well, I mean,
can I jump in? So you verify this only using the commutative relations. You don't need, for example, Dirichlet's prime number theorem or anything like that.
Oh, really?
Yeah, you basically you verify this powerful condition.
Mm-hmm. Oh, powerful, I see.
Yeah.
But you are using elementary matrices.
We do, but we don't need, for example, like Dirichlet's prime number theorem or anything like that.
Yeah, okay, right, which is the way you explained it, right?
Yeah.
Okay, so let's give another two.
Wait a minute. So the question is the question whether for an anisotropic group this PG or PG prime might still be true? Is that the question?
Yeah.
Yeah, I mean, we want to verify this.
You believe the congruent sub property, so Peter, let's explain that PG and PG prime are actually equivalent to the congruent sub property.
Mhm.
And by circumjecture, we do believe that the uniform lattices do have the congruent sub property, so we should believe that they have this property.
Okay, and in this use of the torus and Schmidt subspace, there are effective bounds for the sizes of, as you know, for the number of solutions that can't be used to address this. I guess you've tried.
Probably yes. I mean,
in other words, all I'm checking is you still, as far as anybody knows, PG, well, since it's equivalent to the congruent subgroup property, we all, or you believe that still might be true. Okay.
This is how we expect that as you know, a strategy to attack congruent subgroup property. So yeah.
Another thing is that in principle, you can try to verify this condition on the computer, at least run some numerical experiment. At the same time, I don't know any, you know, reasonable way to try to verify bounded generation on the computer.
Yeah.
Yeah, it's a good point, because you have to find clever generators.
Yeah.
I was going to ask, when you say verifying the computer, do you mean kind of graph the function and see that it looks like it grows slower, or can you actually algorithmically decide whether an assertion like this holds by playing with the generators in some way?
No, you cannot do this decisively, but you can at least collect some numerical data and see whether it holds. While for bounded generation, I see no way really to even collect the data on whether it's likely to have bounded generation or not.
Andre, if you take these quaternion groups, that you take the standard say quaternion algebra and localize the 2 primes, so there is a very nice set of generators, you know this, like P plus 1 element and N plus 1 element,
yeah.
And all the relations are type AI Pj equal to Bj prime AI prime. These are not helpful in order to check property like Bg or Pg or Pg prime.
Well, at some point many years ago, Tim Stiger tried to compute.
Ooh.
And his computations were really that the index does grow like polynomial.
Ah, but then Grunewald, the rumor, I mean, we all understand that Grunewald thought that, I assume with those generators, bounded generation was true, but that was clearly was, he misread his data if he had data. So you say Steiger computed this PG prime for these groups?
Yeah, but not very far. So because his computer ran out of memory, but in principle, I mean, it's possible.
Yeah, that could be very interesting, actually. Yeah.
All right. So let's go to the final slides. So there are some more questions concerning this bounded generation. So if you consider the amalgamated product, well, there is some interesting phenomena appears. So I mean, if you consider this SL2, if you localize at only 1 prime number, so we know that this one has the infinite unit groups. So by our theorem, by the theorem of Morgan, Rapinchuk, and Suri, this one does have bounded generation. And this one is amalgamated products, such as gamma 1 and gamma 2 are both isomorphic to SL2Z. And gamma 0 is the congruent subgroup, which is such as the 2-1 entry is congruent to 0 modulo P. However, if you consider the H to be the usual quaternion, and you consider this the norm 1 group, and if you consider this R, if you localize at 2 primes, this one is also a very similar amalgamated product. Gamma, these 2 groups are virtually free, and I mean both groups are super rigid, and both groups do not have non-central normal subgroup of finite index. So there's a lot of similarities. However, one group has BG, one doesn't. And the reason behind it is not clear at this moment. So, I mean, due to this observation, we would like to see, can we give some condition criterion or some verifiable condition to see when some amalgamated products have bounded generation, or at least, I mean, this polynomial index growth?
Yeah, actually, this is an amazing question you're asking now, because you're completely right. These two groups, I mean, go to a finite index subgroup in both of them, and then both of them are free product with amalgam of a free group with a free group over a finite index subgroup.
Yeah,
And
so
it's kind of an unbelievable that one is bounded generated and the other is not. I completely don't see it from a pure group.
Yeah, and you see this one has no BG. It's exactly our theorem, So the
right. No, that's an amazing observation that looks on like, and it's kind of amazing.
Yeah, makes you wonder whether the theorems you're quoting are correct.
What?
I mean,
joking. I'm joking. It looks like a paradox.
We check everything carefully, and we believe that everything is correct. So there must be some reason behind this phenomena. All right, so let me close this talk by a general question. So, I mean, in the past 40 years, all the examples of semi-simple, that means, the Zariski closure is a semi-simple algebraic group. All the examples of semi-simple linear groups can be, understand as some arithmetic groups. I mean, if this group has bounded generation, so that we wonder if this is always the case. And so we expect some investigation, comes in this direction. All right, that's all. Thank you very much for your attention.
Yeah, let me just recall this, that also in my talk, I ask, can a thin subgroup be bounded generated? I think we don't know any example of a thin subgroup which is bounded generated. Yeah, this was a great talk, Jinbo. Any questions?
Yeah, all questions are welcomed.
Well,
wait, I just, so have you thought, you and Andre and Umberto and Pietro, about when you, the proofs using Schmidt are all ineffective, but the number of solutions and the number of subtori, that's effective. You can bound, so they're not such great bounds, but they are effective. And I wonder if you can relate, if you can quantify any of that in connection with your question of the Siegel variant. Where in other words, you have not seen a Diophantine interpretation. I mean, the great thing, that the way you solved this problem was to understand what the Diophantine content of bounded generation was in terms of Torah. That's how you solved it. Now you have a weaker condition, which is this powers be some growth rate of powers of the subgroups, which is a more quantitative statement rather than purely qualitative statement. But I'm just saying the proofs, the other proofs do have a quantification at the level of the number of solutions. So I'm just saying, is there some heuristics that might be? I mean, at this point, I would be starting to get nervous that the congruent subgroup property is true, even for the quaternions.
I mean, but the subspace theorem is far from effective, right? So,
no, the subspace theorem is not effective, but the number of solutions on the torus and Schmidt and Schlichewey and Everster wrote beautiful papers giving uniform bounds, independent of the field even.
Peter, let me remind you that there are some uniform lattices for which
have the, right.
It was proved. So it would be a huge surprise if some are not, but it will be it goes both ways.
Yeah, but super rigidity went unexpectedly also. Yeah.
Right.
You have to keep an open mind, I think.
Yeah. I mean, I think that we failed here for 30 years because we had the wishful thinking after the work of Platonov and Rapinchuk in mind that they have bounded generation, because that would be a way for the cell conjecture. So we didn't really check for a counterexample. But anyway, good. That's a big, yeah.
Yeah, but so all I'm saying is that the solution to the problem that you don't have bounded generation is invoking some beautiful Diophantine finiteness theorems. And those, I'm just saying, maybe you put in all the so I'm just saying, I'm sure Umberto can quickly analyze this, but there are, more refined conjectures. And if you put those in, maybe it does. It's the first time I've seen this PG property. So I'm just saying.
Okay.
Yeah.
Yeah. Yes. Yeah. Yeah. Okay.
Very good.
Yeah,
very interesting. Okay, those who are here at the Institute are very welcome to join us for a lunch now. Those who are not are welcome to join next week's seminar. So we'll have 2 seminars. At 10 o'clock, Bill Goldman will talk about character varieties and the dynamics of them. And at 11, Will Chain will start a topic which will be several talks. I think they're all already announced on the website of the Institute.
One thing before everybody runs, let me just make an advert here that I think Jacob Zimmerman's giving a colloquium at the university this afternoon. It was announced very late. I can't be there, but they will be Zooming it. And it is on the topic that Jinbo mentioned it's about Andre Ort. So I encourage you all to go.
Yeah.
And great talk. Great talk, Jinbo.
Yeah, very good. Okay, see you soon.
Okay, see you. I will join you in 10 minutes. I'll go downstairs and go to the dining hall. Okay, thank you. Bye-bye.
Bye.
Bye, Jinbo. Bye.
Yeah.